I have several different hats, but I'm speaking as WarpSpace now. At WarpSpace, I have a role as a Chief Strategy Officer of the group. We currently have 3 offices, one in Japan, headquarters, another one in US and Washington, D.C., and soon we will have another office in Europe. Yeah. And I'm CEO of WarpSpace USA as well, and I have to go to US and also talk with people, including some governments and obviously some commercial companies. And what we do at WarpSpace is, as it's written here, we use LaserCom to basically reinforce SATCOM for Earth observation industry. Why we do this? Let me first introduce the issues it's already existing in the Earth observation industry today. Today, you see lots of satellites launch into space, and most of them are actually low Earth orbit. Mostly due, thanks to SpaceX launching the Falcon 9 into Rio. Most of the people do the rideshare launched into low Earth orbit, more specifically sun synchronous polar orbit. And that's pretty good, because it's cheaper. You can launch satellites to the orbit very quickly. But issue is, since altitude is very low, they are orbiting the very fast speed. And most of the, say, ground stations which can communicate with the satellites is located around the Arctic. As a result, to be honest, 90% of the time, satellites cannot really communicate with, say, the Earth, right? So it's opportunity loss at 90% of the time. We actually losing it. And today, people basically use a radio frequency, radio. We we use it for the terrestrial use as well. But in space, if we want to do the radio frequency communication, we have to do registration with local government. Then local government have to talk with ITU, that's International Telecommunication Union. It's under United Nations. And these days, just so many satellites up there. It usually takes 1 to 2 years in order to say register the frequency. That's also paying us for startups. Startups can maybe build the satellites in 1-2 years, but they have to also think about 1 or 2 years for paperwork. That's basically slowing people down. And we calculated the total opportunity loss as a $200 billion US, basically per year, right? But that's where we come in. We are planning to launch small satellites into medium Earth orbit, which is defined as between 2,000 kilometers and 20,000 kilometers, which is above most of our clients below here. So that when we relay the data from LEO to MEO and the MEO to ground, we have less latency, which means instead of waiting for 90 minutes, we can downlink this data near real time. And also we use laser instead of radio frequency, which is considerably faster than RF. I would say around 10 times faster to begin with. And there's technologically possible to actually increase the data rate. So it could be 100 times faster in 10, 20 years, which radio frequency cannot do it. That's electromagnetics. And as I said, radio frequency signals, we have to register it in order to use it. But for laser, it's not regulated yet because no one uses it. Yeah, that's why we are actually planning to establish architecture like this. And for our service, we actually have radio frequency as well for MEO to ground, because I don't want to go into detail, but when there is a say thick clouds, laser cannot go through. So we want to make sure that if laser doesn't work from space to ground, we use RF. And our vision is realizing connected space, and we already kind of benefit from vast network of optical fibers on terrestrial base. Everyone in almost everyone on the Earth can use pretty good high speed network in Japan, Korea, US, UK. Yeah, we can watch 4K YouTube video anytime. But in space, still data rate is much less. I would say on average probably 100,000 times slower in space. And in terms of latency, in space, still people waiting for like hours to get the data. That's actually really say big hardship for Earth observation industry, especially we want to change that. We want to make telecommunication service in space, which is as good as the ground we have today. The market size we are seeing is written here. We calculated from Earth observation industry, global Earth observation industry, which is estimated as $30 billion US. The number is taken from North Star Research. And there is no say specific research to calculate total market size for ground system for Earth observation industry, but usually it's say that around 5% of the Earth observation industry is taken account for basically ground system like KSAT, SSC, those companies. And we are trying to basically take that market. So that's estimated as 1.5 billion US dollar, which is growing at a pace of 10% annually. And well, how could we contribute to Earth society? It's actually numerical way. We work with Earth observation companies. They take imageries using a various spectrum. Doesn't have to be optical. Sometimes synthetic aperture radar, hyperspectral, RF. These days, there are several new frequencies to see some specific stuff on the ground, on the surface of the Earth. And there are like several good applications, but I will pick 3 for now. One is primary sector. Then the Earth observation industry, or actually Earth observation sectors, has been working with, say, agriculture, forestry, historically, especially driven by space agencies. And we have lots of applications. We could just simply increase the amount of data so that, they're going to use more application for this primary sector use case. And the logistics, surely, we still have issues in order to, say, locate any material, say, trucks. Real timeness is very important. We can contribute for that. And more importantly, say, building a resilient society. Today we have, say, unusual natural disaster, especially in Japan. And in order to, say, counteract against natural disaster is understanding what's going on there. And today, well, and several ways actually used, aerial pictures, taking picture from the airplanes or satellite imagery. Those are mainly used for flood, earthquake, forest fire. But to be honest, satellite data, we usually take lots of hours or sometimes days to get the data from, say, national satellites. And if they use our service, they can get the data in, say, 10 minutes, 15 minutes. That's going to drastically change the situation. Government can plan after, say, natural disaster. That's definitely change the society itself. And this is what I actually explained. So today, usually have to wait for several hours, but real-time optical link, we can provide that. Then, Earth observation industry, they can provide the data in 10, 15 minutes. In a way, if they can get the data in 10, 15 minutes, means they can get the data every 10, 15 minutes, which means they can get at least hourly-based imagery data. If some use cases require hourly data, we can provide that. There's some analytics companies can make, probably artificial intelligence-driven solutions to detect something, or basically, giving some insights to the very end clients. This is the business model. We work with Earth observation industry. The logo here doesn't really mean that we are working with them. Some of them we already announced. Those are the companies we directly work with, or we work with. There are several governments we are talking. Doesn't have to be only ESA or NASA or JAXA. We also work with, say, some ministries who are planning to use satellite data. We talk with them, especially in US and Japan. And we indirectly talk with some of the satellite data analytics companies in order to basically gain some, the last mile of the value chain as well. And we have a long-term plan. Since the first bit I already talked. First, say 10 years, we focus on, say, low Earth orbit Earth observation industry, and perhaps space stations as well. There's a say urgent needs today. So we would like to provide the communication capability for them as soon as possible. But from, let's say, when our Artemis plan actually starts, especially on the moon surface, whatever there is, robots or people, astronauts there, they definitely need telecommunication service from theirs. in order to basically say operate the service, just communication, and also say automatic maneuver of the rover. Those always actually requires telecommunication as well. And also for very long term, we would like to provide our lasercom service to Mars as well. Because lasercom is actually advantageous when it comes to very long distance. Using certain modulation and certain technology, we can send the data even to Mars with much less data loss compared to RF radio frequency. We are planning to do those as well. And in fact, we already start working with JAXA, Japanese Space Agency, since 2021. We actually continue working with them for Artemis plan to begin with. And here is the members, and it's worth noting that there are several former director of JAXA working with us, and also 15 years ago, Japan succeeded in lasercom technical academic demo, and there are several members from that team. For example, Professor Takayama, he was also a scientist there. He worked with us, and also there is another advisor, Dr. Todome. He was a project manager of that project. So yeah, we kind of inherit some of the capabilities from Japanese say techs from 15 years ago as well. And we raised this is slightly old information. We haven't announced, but up till Series A, we raised around $10 million, and we have raised Series B last couple months. And total, we would say more than 20-30 million we've raised so far, and we will soon announce a precise amount. And yeah, we already have Washington DC office. Physically, we have our office in since November. So 4-5 months ago, we established one. I'm a CEO there. I'm there like every month. And yeah, if you're from the US, if you would like to talk about with us, yeah, please let me know. I'm there. So that's about it. Thank you for listening, and I think we can go to Q&A.
Perfect, wonderful. So thank you again, Hiro, for presenting and definitely showing us the power of the laser communications. So I have some of the questions here that I would like to ask you as we still have time. So my question is, can you discuss some of the key differences between free space optical communication and traditional radio frequency communication for satellite applications, and what advantages or disadvantages each technology offers? I know you touched upon that a bit regarding the speed as well. So would love to learn that.
All right. So I usually mention, say, 3-4 factors, the main difference between radio frequency and laser optics. Yeah. And first, as I mentioned, the data rate is a lot different. I think most of the audience here may be familiar with SATCOM radio frequency, but there are several bands: L band, C band, KU band, K band, K band, right? And recently, I think the best performance was KA band. They can do 1 gig max, I think 1 gig, perhaps 2 gig, depending on the technology they have. And the last say frontier for our radio frequency is usually Q band and V band. The maximum capacity for RF is probably just few gigabit per second. That doesn't change. It's electromagnetics. Frequency is just defined. But lasercom, we can do, easily starting from single gigabit per second. We can do 10 gig, 100 gig. And if we just reinforce the lasers by basically stacking up, we can do 1 terabit per second as well. So that's a lot different. RF can do 1,000 times 1,000 RF. That will be able to do with laser. That's big difference. Secondly, it's not technology, but the regulation, right? RF is heavily regulated today, especially because certain bands are really used up by certain major SATCOM companies, constellations, especially KU, K. It's almost some certain band is almost impossible to register it. So even if there is antenna, ground stations, you can't use it anymore, right? That's big disadvantage of RF. And thirdly, security is also something. RF, it's like a flashlight, right? You emit to certain area, and anyone within that area can at least receive it. And if they can decrypt it, they can steal the data. But lasercom, in order to do the communication, we first have to establish a link. It's point to point, very laser point. It's like a point to point. Only one terminal can get the data. So it's safer for certain use cases. Yeah, those are, I think, the difference. And well, I would, courageously mention the disadvantage of lasercom is crowds. Yeah, RF, it depends, to be honest, but most of the radio frequency can go through the crowds, right? But laser can't. So we have to be careful when it comes in space. There's no crowd, so it's easy. But if we wanna do the space to ground communication, if there's a very, very crowded area, we have to be careful. So what we could do is probably geodiversifying the location of optical ground station. Then some last mile could be done by, say, submersible cable. That's the plan, not just us, but other companies.
And can you discuss some of the potential cost savings also that the laser comms can offer to satellite operators?
Definitely, yeah. So thank you for the question. And yes, and I forgot to mention, in terms of, say, cost effective bit of lasercom is, well, actually a lot. Swap is definitely better compared with RF. So swap means size, weight, and power, right? It's lasercom is, like a data rate per power consumption is much better compared with RF. And the size of the terminal is usually smaller. Yeah, most of the RF antennas, everything usually is like several tens of liters, but lasercom maybe 10 liters or so. So that's better. And also weight is also proportional to my size as well. So it's better. And a smaller swap means also less launch cost as well, right? So that's cost effective as well. And also give more space for spacecraft. They can put other, say, sub-missions or main missions. So it's absolutely better in that way. Yeah.
Perfect. And my next question, Hiro, for you is if you can also describe some of the potential applications of laser communication technology beyond just SATCOM, such as inter-satellite links, for example, and deep space exploration, or any other area that you would like to highlight.
Oh yeah, yeah. So yeah, inter-satellite links. Yeah, we do. So that's one thing. But for very long distance deep space communication, also we are actually actively looking into that with JAXA, and also NASA is looking into that as well for LunaNet. And well, there are actually several use cases on especially in space, such as even lunar surface. They like between lunar surface and lunar orbiting stations. Definitely they can do lasercom. There's no atmosphere. It's much easier. And even on the, say, lunar surface, there's no atmosphere, right? Between the, say, facility or base, if we could use a lasercom, it's definitely much faster than radio frequency. Yeah. So that's actually one thing, is the backbone communication on the moon. If there are some bases and separated areas, in order to have, say, very broad backbones, it's better to use laser instead of RF. It's most cost effective. Yeah.
Perfect. Perfect. So thank you again, Hiro, for highlighting again those importances and use cases. And my last question is, as we still have some minutes, so I'm going to ask you another question or two, maybe. So what kind of testing and validation processes does WarpSpace use to ensure the reliability and performance of its laser communication systems under various operating conditions?
Sure. And well, most of the, say, real, how can I say, the physical demonstration will be done on ground. So putting the, say, lasercom terminal on the ground and do the testing at the several kilometers distance to check the data rate, etc. And but from that operation bit, since we are operator, not manufacturer of terminal, we are making, say, virtual software for this relay as well, because actually, in order to optimize the routing, Yeah, it's actually complicated. We work with several different Earth observation operators, and we are in MEO, which is unique orbit. Not so many operators has done that. So we are doing more simulations on desktop basis before we start the service. Yeah. So that to verification we are doing. Yeah. But in the end, we have to do the verification in space, which will happen in 2 years with our first satellites.
Perfect, thank you. And the last question probably then for today for you, Hiro. I know I'm asking you many questions, so I hope you don't mind. So as the laser communication technology continues to evolve, what kind of developments do you foresee that could push the boundaries of current capabilities and open up new business opportunities?
Well, I would say, well, firstly, this laser com say trend was driven by SDA of the Pentagon, to be honest. So that's why they're like a bulk order from the SDA to several companies, so hundreds of orders. That's and also SDA made certain standards that help commercial industry with some of the, how can I say, interoperability bit as well. So it's already starting, and soon the bunch of satellites going to be launched and will be tested. Terminal will be tested. And once people are confident in the usability of the terminal, yeah, then people start using it because it's simply better than RF. It's still people skeptical in a way whether optical terminal works. That's the biggest hurdle of laser com industry today in space. So we'll say that this year, the SDA started to launch satellites, so several tens, right? And then the result will come later this year or next year. Then that result definitely give lots of impact in the whole industry. Yeah.